Hey, this is Travis with Tech UXD, and today I want to talk to you guys about something called a driver's analysis. And a driver's analysis tells you how a set of predictor variables influences or impacts an overall outcome variable. And this can be utilized on your market research data or UX data, survey data. So, for example, a driver's analysis for overall app satisfaction would tell you which aspects of your app or the features within the app most significantly impact overall satisfaction with that app. And this has implications for your product development team. So you can figure out, which areas you want to first improve to get the most bang for your buck in improving overall app satisfaction. So it's a really interesting technique. And I'm going to actually walk you through an example of my code in R and actually the steps that I use to conduct a driver's analysis using the overall app satisfaction example. And at the end, I'll also touch on some other areas where it can be applied, like in market research and customer experience. So before we dive into our example, I want to quickly touch on some fundamentals with the driver's analysis, like what is happening in the background. So I'll be really quick with this stuff, but the driver's analysis is driven more or less by a statistical technique called a multiple linear regression. So let's come over here and look at the scatter plot. We have a y-axis and an x-axis, and these points are individual users from our survey data that we have. So the y-axis is our outcome variable, overall satisfaction with the app, and the x-axis is, let's say, satisfaction with one of the features within the app. Let's call it feature A. So you can see that as their satisfaction of feature A increases, their satisfaction of overall app increases as well. This is somewhat what we would expect. And what a linear regression is doing is fitting a red line. This red line is the actual model, statistical model that it's fitting, as best as possible to this scatter plot data. Now, this is we're using just one variable, in this case, one predictor variable, which is satisfaction with feature A. We could add many more predictor variables in. So let's say the app has 4 features total: feature A, feature B, feature C, and feature D. And we want to account for the satisfaction of all of them in trying to predict overall app satisfaction. So we could continue to add these predictor variables in, and of course we can't visualize this anymore in 2D or 3D because this is now a 6-dimensional multiple linear regression. But we can actually come over here and we can look at the how the model is described mathematically here. So y is our outcome variable. This is the overall app satisfaction. Beta naught, that's just a constant. We can forget about it. X1 is our first predictor, so satisfaction with feature A, satisfaction with feature B is X2, and so on. And these betas are called beta coefficients. So these betas are ultimately what we're going to be interested in, because as you can see, the larger the beta, it's a larger multiplier of the predictor variable. And so comparing the magnitude of the betas will tell us the relative importance of the predictor variables in determining the outcome variable, which is overall app satisfaction. Let's say we get 1,000 respondents. We take them through a usability test of an app. And within this usability test, we basically showcase the major features within the app. So it could be feature A, feature B, and feature C, and feature D. So 4 main features. And once they see those features, we'll have the user rate their satisfaction with them on a scale from 0 to 100. After that, we are going to have them rate their overall satisfaction with the company. So that will be a 0 to 100 scale again, and we'll call it a customer experience score. And finally, at the very end of the usability test, we'll have them rate their overall satisfaction with the app. Coming over here again, you guys are familiar with the general equation for a multiple linear regression. And this is the equation in our example right here. We have 5 predictor variables, each with their own coefficient, CX score, and feature A through feature D. And we are trying to understand their impact on overall app satisfaction. So my hypothesis as a researcher is that the customer experience score and feature satisfaction ratings impact the overall satisfaction with an app. The null hypothesis is that all of the predictor coefficients are equal to 0, meaning that none of the predictors have a statistically significant impact on the overall satisfaction of the app. And the alternative hypothesis is that at least one of the predictors has a statistically significant impact. It's helpful to get all of the variables for your model into one data frame. So I have the first 5 columns here are our 5 predictor variables, and then the last is overall satisfaction, and this is the outcome variable. We have to test that our data meet certain assumptions. The first assumption is that each variable follows a normal distribution and that there is a linear relationship between the predictor variables and the dependent variable because we're fitting a linear model to them. So the histograms show us here that they do follow a normal distribution. The outcome variable is plotted against all the other predictor variables. And we can see here that it does appear to be a linear relationship. These are tight elliptical clusters, and they are oriented up and to the right, which means that each of the predictor variables have a positive correlation with the outcome variable, and that's what I would expect. Intuitively, you would understand that as satisfaction with the features increases, so does satisfaction with the overall app. Another assumption is that the predictor variables are not highly correlated with each other. If they are, this brings up a problem called multicollinearity, and it makes it hard for your model to have precise estimates of the coefficients. It just decreases the precision of your model. So just realize that this could be a problem, but we will check this later on once we fit the model. Okay, and actually the last assumption here is that all of the predictor variables have to be on the same scale as one another. So if the feature satisfaction ratings were on a scale from 1 to 7, and the customer experience score was on a scale from 0 to 100, this would be a problem. So you want to standardize your predictor variable scales so that you can interpret the model easily at the end of all this. Now we've checked the data and we're ready to actually fit the model. So I just wanted to show you guys how quick and simple it is to do this in R. The function is LM, linear model, and you specify your outcome variable, overall satisfaction, tilde, and then this period means use all other variables in the data set as predictors. The model has been fit, but there are also more important assumptions that we need to make sure to check. The residual should follow a normal distribution. Okay, let me back up and talk about residuals. Our model can now make predictions of the outcome variable. That's what a model is. It takes the predictor variables as input, and then it will output a prediction. The predicted value minus the actual value is an error term, and that's called a residual. Residuals should follow a normal distribution. There should be no pattern in the residuals across the model's predicted or fitted values. And we need to be careful about outliers because this can affect the model estimates. And again, we'll check multicollinearity. But before we do that, first assumption right here, residuals follow a normal distribution. We can see that they line up on this 45-degree red line on the QQ plot. This is checking normal distribution. And this first column here helps us check the second assumption, which is that there's no pattern in the residuals across the model's fitted values. So you can see that this red line right here tracks really closely with this straight horizontal dotted line. And same thing down here for the standardized square root of standardized residuals. So we can see that the assumption number 2 has been met. Finally, this fourth plot down here in the fourth quadrant is checking for outliers because outliers can really affect the model coefficients. So like, let's say one of your users is typing in their overall app satisfaction and types 10 instead of 100. Well, if you leave that observation in the data set, then it can impact the model overall, which you don't want, especially for something caused by a data entry error. So this plot just helps you make sure that no single point is really skewing the model estimates. This is when the predictors are highly correlated with one another, and it hurts the precision of the model. It's difficult for the model to tell the difference between two variables if they're like 99% correlated. I mean, how could you tell the difference? What we do is we calculate something called a variable inflation factor, or VIF. And this gives us a VIF score for each of the predictor variables. And, different sources say different things, but generally they should be below 5 or 10. So luckily, we came in right under with feature C. So I'm going to just say that we don't have any multicollinearity issues. If you guys have VIF scores higher than this, then maybe think about thinning out your predictor set, the variables that you actually put into the model. And try to remove variables that are highly correlated with one another. Okay, finally, we're past most of the drudgery in linear regressions, and we can actually look at the summary of the model and basically the results of the model. What is it telling us? It's fit the model now, and it's giving us coefficients for each of the predictor variables. This is cool. So this is the summary of our linear model object in R, and I'm just going to point to some specific places, highlight some specific places that are of interest. First of all, the F statistic down here is measuring the statistical significance of the overall linear regression. So this p-value is really small, and what that is telling us is, going back to our original hypothesis, the null hypothesis is that none of the predictor variables are statistically significant in predicting overall satisfaction, and the alternative is that at least one is. So we reject the null hypothesis based on this very small p-value and accept the alternative hypothesis, which is at least one of our predictors is significant. Now, this doesn't really tell much, so at this point but this is an initial check. So if the p-value doesn't meet your criterion of, say, 95% confidence interval, then just throw this model out because it's no good. But now that we know that something is interesting in here, we can go look at the specific predictors in here. So you see each of these rows are each of our predictor variables. This estimate column is the beta coefficients that multiply each of the predictor variables. And we are running an individual t-test to test statistical significance for each of the predictors. So these asterisks over here are saying that this is highly significant, feature C is highly significant, feature D is. Feature A is close, but it's still significant at the 95 CL, and feature B is not. But that's okay, because we'll actually handle this in our analysis. So this is just kind of an initial look at the summary for linear regressions. Here's an interesting term down here. I don't want to get too far into this, but adjusted R squared, it's basically a measure of how well your model fits the data. So as your error terms increase, as the residuals increase, your adjusted R squared is going to decrease. And so the literal interpretation of adjusted R squared for us right here is that 52% of the variance in overall app satisfaction is explained by our predictor variables. So 52% is explained by our model, but 48% is unexplained variance. It's easy to think about other variables you can add in for explaining more of the variance. Like, for example, if we added, let's say this app was for Gen Zs. It's something similar to TikTok, right? So you would expect Gen Zs and millennials to give higher scores than baby boomers or Gen X who are rating this app. So if we added an age variable in, I would predict that the age variable would have a negative coefficient here, because it's saying that age is inversely proportional to overall app satisfaction. And I would expect the adjusted R-squared to increase because adding this age variable is going to explain more of the variance in overall app satisfaction. This coefficient plot is interesting. It's more for visual people. And what it's doing is on the x-axis, it is showing us the beta coefficient values for, on the y-axis, each of the predictor variables. And these horizontal lines are the confidence interval for the coefficient estimates. So definitely we see that CX score and feature C stand out from the rest of the pack in terms of high beta coefficients. And we have some others here that are definitely still significant. And as we said before, feature B has a coefficient very close to 0, so it may or may not be statistically significant. All of these coefficients are greater than 0. That makes intuitive sense because, as we've said before, as overall feature ratings are increasing, we would also expect overall app satisfaction to increase as well. It wouldn't really make sense to me if some of these features had negative coefficients, which means as the satisfaction with a feature increases, overall app satisfaction decreases. That doesn't make too much sense to me, so I'm happy to see that it's intuitive here. All predictors are statistically significant at the 95% confidence interval except for feature B, okay? All coefficients have a positive sign. We just talked about that. This makes intuitive sense. Awesome. Number 3, CX score and feature C have the largest coefficients by far. So this is definitely going to fit in somewhere in our final analysis or recommendations to the product team. And the 4th is that the 5 predictors explain 52% of the variance in overall app satisfaction. Now, a quick disclaimer here. 52% variance is really high. 0.52 is really high adjusted R-squared, especially for behavioral and human sciences. When you're modeling human behavior, it's really hard to explain this much variance because human beings are so difficult to predict and sort of random. So I would say that an adjusted R-squared of 0.3 is definitely still really solid. And remember that I simulated this data. So really, I would not expect your adjusted R-squareds to be as high as mine here. Just a quick note on that. Okay, we're through everything now. We have our model, we understand what it's telling us, and now it's time to talk about specific recommendations that are going to come out of this driver's analysis. So let's say that we're presenting to the product team or the product development team, and we're trying to prioritize which features we want to focus on improving in order to most significantly improve overall app satisfaction. So we have the beta coefficients. This tells for each predictor variable, and this tells us how important, basically the relative importance of the predictor variables. And also to make it a little more of a sophisticated analysis, we can actually look at the average satisfaction for each of the predictor variables and see where we're at right now in terms of satisfaction for each. So looking at this product development decision matrix, that's what I called it here. X-axis is average satisfaction of predictor variables, and y-axis is beta coefficients. Okay, so again, beta coefficients is a proxy for how important, the relative importance of the predictor variables, and satisfaction. We can see that some have lower satisfactions than others. So the CX score has a high satisfaction and high beta coefficient, which means that it's highly impactful, but it's already high satisfaction. So maybe it's going to be difficult to continue to improve the satisfaction here. In any case, it's a strong suit for us, this customer experience score, and maybe it should be marketed more, or maybe it should be improved. The most interesting quadrant is definitely quadrant 2, because we see that feature C is relatively low satisfaction, but relatively high in terms of importance here. So what I would say to the product team is that they should prioritize their efforts on improving feature C, because this will give them the most bang for their buck in improving overall app satisfaction. Okay, just a little more down here. Feature D has low satisfaction and a low impact, so it's not super important. If it can be improved, I would say definitely do it, but it will be low on the list in priorities. Feature B and feature A have high satisfaction and low importance, so they should be maintained but with minimal effort. Again, we're focusing most of our attention here on feature C, and this is the main recommendation for our drivers analysis. There are many other drivers analyses you can do besides that, and so I want to talk briefly about how to select your outcome variables and predictor variables. Really, your outcome variable can be anything that is any metric that is of interest to your company that your company wants to control or improve. And I'll give you some examples in a second here. And the predictor variables should be, you as a researcher should be coming up and designing a survey to collect predictor variables that you think might impact or influence the outcome variable. So let's talk about some examples over here in the market research and customer experience space. We've got net promoter score, we've got customer effort score, we've got customer satisfaction scores. These are more brand and company level metrics. And a lot of companies track these over time to see whether or not they're increasing or decreasing. And so it'd be really interesting if you could come up with a driver's analysis to figure out what is driving a high or low NPS score or a customer satisfaction score. I actually found some pretty interesting examples on the internet of a net promoter score driver's analysis. Let's see. Yeah. So, so the outcome variable for this was net promoter score. How likely are you to recommend this company to a friend or family member on a 0 to 10 scale? And then here are the predictor variables. They're basically brand attribute ratings. Is the brand fun? Is the product worth what you paid for? Is it innovative? Good customer service? Stylish? Easy to use? And this yes right here means that it's basically a binary variable. So it's either yes or no. This is categorical. In our example, I used numeric variables, 0 to 100 scales. But in regressions, they're real flexible, and you can use either categorical variables, numeric variables, or a mixture of both. So, feel free to experiment with the different predictors that you include. This website also ran a net promoter score drivers analysis, and they used a different set of predictor variables. These are ratings over the customer journey. So different customer touch points like the website experience, live chat, shipping, customer service. And they're using these as predictors to try to understand what drives the net promoter score. And they actually have already done an analysis here, and they see that the website experience was a key driver. So I'm sure that they'll go back to their product teams and explain why they need to update their website. Okay, also, we had a product development example. There's also usability examples, I think. So you can run a usability test where, let's say you have 10 tasks and you are recording the user performance on each of the tasks. And then at the very end, you have a system usability scale, the SUS. It's 10 questions, and it generates an SUS score from 0 to 100. And the SUS score is a proxy of the usability of your app. So this is really interesting because, just coming over here, let's say that you did a task-based usability test with 10 tasks, and you are determining, and then for each of them, it's did the respondent pass or fail? And this is the percentages right here. So you can use these pass-fail predictor variables to try to predict the overall SUS score. And this would tell you which tasks or which aspects of your app most significantly contribute to app usability and most significantly detract from app usability. So I'm sure it would be an interesting test. Yeah, thanks guys for watching. I hope this helps. And if you guys have any questions, just direct message me or post them in the comments. I'd love to get a discussion started on how we can start utilizing some of these statistical techniques more in UX, market research, and product management. Thanks.